Hi, good morning all. Welcome to the Electronic Circuits 1 class. In this class, we are going to discuss about the first unit, and the topic of first unit is biasing of discrete BJT, JFET and MOSFET. And the topics we are going to see is BJT, need for biasing, DC load line and bias point, DC analysis of transistor circuits. These are the topics we are going to see. First, let us discuss about what is a BJT. The BJT stands for bipolar junction transistor, and it consists of a silicon crystal in which a thin layer of N-type silicon is sandwiched between two layers of P-type silicon. So there are two PN junctions in a bipolar junction transistor, and the current conduction is by both the majority and the minority carriers. So it is a bipolar device. A layer of P-type material is sandwiched between two layers of N-type material. So this is symbols of NPN and PNP transistor. And a transistor biasing, how a transistor should be biased. The emitter base junction should always be forward biased, and the collector base junction should always be reverse biased. So this is how a transistor should be biased. So this emitter is a positive terminal, base is negative. So emitter base forward bias means emitter is connected to positive terminal and base is connected to negative terminal. Similarly, base collector junction is reverse bias. Base is negative and collector is positive. So here N-type base is connected to positive terminal and P-type collector is connected to negative terminal. So this is how a transistor should be biased. Emitter base junction forward biased and the collector base junction reverse biased. Okay, so this is the thing which we have discussed. Usually the emitter base junction is forward biased and the collector base junction is reverse biased. Okay. So this is how a transistor operates. Due to the forward bias in the emitter base junction, and emitter current flows through the base into the collector. So the entire emitter current flows through the collector circuit. So now coming to the bias stability, the quiescent operating point of a transistor amplifier should be established in the active region of the characteristics. So if our transistor to operate stable, we have to fix the bias point. Okay, so the quiescent operating point or bias point of a transistor should be established in the active region of the characteristics, and basically three parameters, that is beta, the current gain, IC0, the reverse saturation current, and the VBE, base emitter voltage. So these are the transistor parameters which are functions of temperature, and the operating point shifts with changes in temperature. So these three parameters are dependent on temperature. And due to variation in these three parameters, the collector current varies, and due to the variation in collector current, the operating point shifts with changes in temperature. If the operating point shifts, the transistor will not act in the stable region. Okay. The stability of different methods of biasing transistor circuits and the compensation techniques for stabilizing the operating point are going to be discussed. Need for bias. Excuse me. In order to produce distortion-free output in amplifier circuits, the supply voltages and resistances in the circuit must be. What is the need for biasing? In order to produce distortion-free output in amplifier circuits, the supply voltages and resistance in the circuit must be suitably chosen. These voltages and resistance establish a set of DC voltage. So fixing the operating point means we are fixing the voltage VCEQ, that is collector to emitter voltage, and the current ICQ, that is collector current ICQ. So VCEQ and ICQ, that is called the bias point to operate the transistor in the active region. These voltages and currents are called quiescent values which determine the operating point or Q point for the transistor. The process of giving proper supply voltages and resistances for obtaining the desired Q point is called biasing. So biasing means setting the proper supply voltages and resistances to obtain the desired Q point. So the circuits for getting the desired and proper operating point are known as biasing circuits. So this is the equation represents the collector current equation, that is IC equal to beta IB plus ICE0, where ICE0 is a reverse saturation current. Okay. So we are replacing ICE0 with 1 plus beta into IC0. Okay, beta IB plus 1 plus beta into IC0. So here there are three variables, HFE, that is beta, IB and IC0 are found to increase with temperature. That means for every 10 degree rise in temperature, IC0 doubles itself. So when IC0 increases, IC increases significantly. This causes power dissipation to increase and hence to make IC0 increase. So again the IC0 increases. This will cause IC to increase further, and the process becomes cumulative, which will lead to thermal runaway. So that problem is called thermal runaway, that will destroy the transistor. So in addition, the quiescent operating point can shift due to temperature changes, and the transistor can be driven into region of saturation. So the effect of beta on Q point is shown in the figure. One more source of bias instability is considered to be VBE. There is base emitter voltage. So normally the V base emitter voltage is 0.6 volt for silicon transistor and 0.2 volt for germanium transistor at room temperature. So as the temperature increases, the base emitter voltage decreases at the rate of 2.5 millivolt per degree Celsius for both silicon and germanium transistor. So how for every 10 degree rise in temperature the IC0 doubles. So here the variation of VBE with temperature is VBE decreases at the rate of 2.5 millivolt per degree Celsius. Okay, so the transistor characteristic curve shifts to the left at the rate of 2.5 millivolt per degree Celsius for increasing temperature, and hence the operating point shifts accordingly. So to establish the operating point in the active region, compensation techniques are needed. Okay, so this diagram shows the effects of beta and Q point. So the x-axis shows the VCE and y-axis shows the VCC by RC. And this diagram shows the transistor amplifier circuit. So here we have the base resistance and the collector resistance. Okay, so how to draw the DC line? So let us see how to draw the DC load line. So considering this circuit diagram, we can write the equations as VCC equal to ICRC plus VCE. VCE represents collector emitter voltage. Okay, so here I am moving the mouse. So VCC equal to ICRC plus VCE. So since emitter is ground, so here just VCE. Okay, so now you draw a graph taking VCE on the x-axis and IC on the y-axis. Okay, so and mark the points that is VCE equal to VCC. So here VCE equal to VCC and IC equal to VCC by RC. So here IC equal to, so in this equation first to put IC equal to 0. Put IC equal to 0, that means VCC equal to VCE. So mark that point, that is VCC equal to VCE equal to VCC, and then in this equation put VCE equal to 0. So IC equal to VCC by RC. So mark that point, that is let us represent 3.5 milliamps. So that is called, that join these 2 points, 3.5 milliamps and 21 volts. If you join these 2 points, that is called the DC load line, and the center point may be called as, may be fixed as the Q point. Okay, so that represents 1.5 milliamps and 12 volt. Similarly, a AC, this is called the DC load line, and an AC load line may be drawn by including this load resistance. By including this load resistance, we can draw the AC load line, and that intersects as this 24 volt 3 milliamps. So the intersection of the DC load line and the AC load line gives the quiescent operating point, or Q point. Okay, so this is how we have to draw the DC load line and AC load line, and I have explained it. Okay, this all the things I have explained. Next we will discuss about the fixed bias circuit. So this is the DC load line and AC line. Then we discuss about the stability factor. So what is defined by stability factor? Stability factor is defined as the rate of change of collector current with VBE, keeping IC0 and beta constant. So 3 parameters vary with temperature. So that is VBE, IC0 and beta. So the stability factor is defined as the rate of change of IC with any one of the parameters, keeping other parameters constant. Okay, so first let us define S. S may be defined as rate of change of IC with IC0, keeping VBE and beta constant, and S dash may be defined as rate of change of IC with VBE, keeping IC0 and beta constant, and S double dash stability factor is defined as rate of change of IC with beta, keeping IC0 and VBE constant. So this is how we have defined expressions for S, S dash and S double dash. Okay, so write dou IC by dou VBE, keeping other 2 parameters constant, dou IC by dou beta, similarly dou IC by dou IC0. So this is how we are defining the stability factor. And now let us consider the biasing methods. First let us see the fixed bias method. In the fixed bias method, a base resistor is connected from the base to the power supply VCC. So this is the circuit for fixed bias circuit. And let us derive the expression for stability factor. So S equal to 1 plus beta by 1 minus beta into DIB by DIC. Okay, so in this equation, so first VCC equal to, we have seen VCC equal to IBRB. So you have IBRB plus VBE. So coming to the input circuit, IBRB plus VBE. So from this you find the value of IB. IB equal to VCC minus VBE by RB. So now you find the stability factor from this. S equal to 1 plus beta by 1 minus beta into DIB by DIC. Here DIB by DIC is 0. Okay, so the denominator becomes 0, so S equal to 1 plus beta. So the stability factor for a fixed bias circuit is 1 plus beta. Since beta is a large quantity, this is very poor. So suppose beta equal to 50 means the stability factor is 51. So the stability factor is very high for a fixed bias circuit. So this circuit is not commonly used. Okay, this is the thing. The advantages of this fixed bias circuit are simplicity, small number of components required, and if the supply voltage is very large as compared to VB of the transistor, then the base current becomes largely independent of the voltage VBE. So these are the advantages of fixed bias method. Next we will discuss about the emitter feedback bias. In this emitter feedback bias, an emitter resistor is existing. Okay, so here there is an emitter resistor and other components are same as the fixed bias circuit. So a base resistance is connected to power supply VC and a collector resistance is connected to the power supply VCC, and emitter resistance acts as the feedback resistor. So this acts as the feedback resistor which reduces the collector current on increase. Okay, so now let us derive the equation. So it contains an emitter resistor for improving the stability level over that of fixed bias configuration. So here the stability is improved than when compared to the fixed bias. Okay, so this base emitter loop VCC minus IBRB minus VBE minus IERE equal to 0. So taking there are two resistors IB plus IC into RE. So look at this circuit. So through RE two currents are flowing, IB plus IC. Okay, so that is what we have written, IB plus IE. IE is IB plus IC into RE. Okay, so the solving we are able to get IB equal to VCC minus VBE by RE plus RB minus RE by RE plus RB into IC. Now when you calculate DIB by DIC, it becomes minus RE by RE plus RB. So okay, here the first term will become 0 since there is no collector term. So first term will become 0. Second term we have minus RE by RE plus RB. So substituting in the expression for stability factor, we have 1 plus beta by 1 plus beta into RE by RE plus RB. Okay, so that means here 1 plus beta. So for the fixed bias circuit, the value is just 1 plus beta. So here it is reduced somewhat by the denominator term. Here it is, since the denominator term is greater than the numerator term, here the stability factor is reduced with the case of emitter feedback circuits. A better thermal stability is achieved compared to fixed bias circuit in the emitter feedback method. Okay, next one is collector emitter loop. So in the collector emitter loop, so this is a circuit diagram for collector emitter loop. We have this is with the previous circuit only. We have written the expression in the output side. So IERE plus VCE plus ICRC minus VCC equal to 0. Deriving, we are applying VC equal to VCE plus VE. Okay, so here we are writing the output equations from the output side. VB equal to VBE plus VE. Okay, next circuit. So we have seen two biasing circuits. One is fixed bias or base bias, and another one is emitter bias. Next, the third category is collector to base bias or collector feedback bias. So here what we have done means, from collector to base there exists a feedback resistor. So previous case for fixed bias circuit we took this base resistor from the VCC. Here we took the base resistor from the collector. So there exists feedback from collector to base. So it is called the collector to base bias or collector feedback bias. So previously here in the emitter bias there exists an emitter resistor which provides us a feedback. Here we have taken a collector resistor and collector to base bias. Okay, so this is called collector feedback bias. And similarly we have to write the expression for VCC, and then we have to derive what is dou IB by dou IC, dou IC by dou IB or something like that. Okay, so this is the loop equations, and we have derived the expression for stability factor S equal to 1 plus beta by 1 plus beta into DIB by DIC. So when you consider this, DIB by DIC is RC by RC plus RB. So here 1 plus beta by 1 plus beta into RC by RC plus RB. So here also compared to stability factor of fixed bias, so here we are having reduced stability factor. So here also the stability factor is reduced. Okay, so here also improved stability factor. Next one is collector to emitter feedback bias. So collector to emitter feedback bias. So here we have the collector to base feedback resistor. In addition, we have another emitter resistor here. So the stability improves further. So there are two feedback paths. One is through collector and another one is through emitter. So there are two feedback paths, collector and also emitter. So how much they do? So here we have RE plus RC. So the differentiation of IB with IC will be RE plus RC by RE plus RC plus RB. So still the stability factor improves. So 1 plus beta into RE plus RC by RE plus RC plus RB. So the stability factor improves still for